Today we are going to see the third module of nucleophilic substitution at aliphatic carbon, and in this third module now we are going to talk about Sni type of reactions, then the rearrangements in SN1 reaction, and then compare SN1 and SN2 reaction. So let us go first for Sni type of reactions. Sni indicates it is a internal nucleophilic substitution. Some people also call it as intramolecular nucleophilic substitution reaction. Now, this is a special type of substitution reaction which is very rarely observed, in which generally alkyl chlorides are obtained from alcohols. And the speciality of this particular reaction that it goes by retention of configuration. So we have seen SN1, in which we found that there are when the reaction takes place, there is both inversion as well as retention. In SN2 reaction, there is exclusively inversion of configuration, whereas Sni type of reactions are there where retention of configuration is observed. Generally, this reaction is observed whenever alcohol reacts with thionyl chloride. So, if I take an alcohol and react with thionyl chloride, that is SOCl2, then it is observed that first it forms its ester. This thionyl ester then further can undergo all types of reactions, that is SN1, SN2 and Sni, depending upon what is the reaction condition. Generally, it undergoes Sni and SN2 type of reaction. So, we are going to focus our attention on Sni type of reaction. So, here you can see that this particular ester formed, then breaks down, forms an intimate ion pair. You can see here, you have a carbocation and you have an anion, very close to each other. So we call this such kind of species as intimate ion pair is formed, and then the Cl of this particular group attacks from the same side, and you get alkyl chloride as a product with evolution of sulfur dioxide gas. So this reaction proceeds via a retention of configuration. Now during same reaction, if I add pyridine in that, okay, the pyridine reacts with this ester and changes the course or the mechanism of this particular reaction. Now you can see when pyridine reacts, you get this kind of ester, and now the chloride is free to move. This chloride now, instead of attacking from the same side, now attacks from the back side, and you get a product where now there is inversion of configuration because reaction goes via SN2 mechanism. So whenever alcohol reacts with thionyl chloride, if I add pyridine into that, you get a product with inversion of configuration because the reaction goes via SN2 mechanism. Or if I add a dioxane, again you'll find that reaction goes via SN2 type of reaction, but you get a product with retention of configuration. But if these two things are not there, then normal reaction, Sni reaction, where you get a product with retention of configuration. So if I want to check the mechanism, see, let's say this is our substrate, this is the alcohol, and is going to react with this thionyl chloride molecule. So the first at OH of your alcohol will attack this thionyl chloride and gets converted into this species. Now an ester is formed, or you can see here you get this intermediate, this is a protonated chlorosulfite is formed, and then in next stage what happens, there is a deprotonation. This chloride which is released takes up this hydrogen, and you get an chlorosulfite ester is formed. This chlorosulfite ester, after formation, now OH, which was bad leaving group, is converted into a good leaving group. Now this can depart from this particular substrate and you get a intimate ion pair formation where your positively charged substrate, that is a carbocation, is formed, and your this O associated species remains in vicinity with each other. It is not completely bonded, it is not completely detached, they are very close to each other, and now a Cl is going to attack this particular carbocation. But what is the difference? That this Cl will attack from the same side of the leaving group. This was the side of leaving group, beta side, and Cl will also come from the beta side, and you will get the product where now Cl is attached to your substrate from beta side, and then sulfur dioxide gas will be evolved. So this is how this Sni type of reaction takes place. So to summarize, you get an alkyl chlorosulfide whenever alcohol reacts with SOCl2. The second step, the concerted loss of sulfur dioxide molecule and its replacement by chlorine, that is chloride, which can attach to the sulfide, which is attached to sulfide group. So what is the difference between SN1 and Sni? So SN1, you get complete just carbocation species, but in Sni you get ion pair, intimate ion pair is formed. Because there is an intimate ion pair, you get a product exclusively with retention of configuration, and because in SN1 carbocation is formed, there are two possibilities that the nucleophile can attack from the same side of leaving group as well as from the back side, rear side of the leaving group, and therefore there you get both retention and inversion of configuration. So this is how we can distinguish between SN1 and Sni type of reaction. Now again we will be talking about little more details about this SN1 type of reaction. It is observed that this Sni type of SN1 type of reaction many times proceed with the rearrangement. That means you get a product where unexpected product, and you'll find that the product is obtained with the rearrangement. How? Let us see that. So let's take an example. 2-bromo 3-methyl butane. This is a secondary alkyl halide. Whenever heated in presence of ethanol, you are expecting that a Br will be replaced by your nucleophile and you will get this product. But it is observed that you don't get this product, but you get this product. Now this product is a rearranged product, whereas this is your normal product, which is the expected product. So how this happens? If you see the mechanism, you'll be able to understand how it happens. So for example, if I take a neopentyl bromide, this neopentyl bromide is a primary alkyl halide, and we know that primary alkyl halides generally undergo SN2 type of reaction. But if you take this particular substrate, the backside attack of the nucleophile is just impossible because it is attached. This particular alpha carbon is attached to a bulky group, that is tertiary methyl group. So obviously this particular substrate is forced for SN1 type of reaction. Now if it goes via SN1, what you will find, the Br will go as a leaving group and you will get a primary carbocation. And we know that primary carbocation is highly unstable. So in order to increase the stability of this particular carbocation, this particular intermediate undergoes rearrangement. Now what is this rearrangement? So in this rearrangement, one of the group attached to beta carbon is shifted to this alpha carbon. Generally hydrogen or methyl groups are shifted, and so that you can obtain a more stable intermediate or more stable carbocation. So if you see here, now here we don't have any option. There are 3 methyl groups, out of which 1 methyl will be shifted to this particular carbon, and you will get a carbocation now which is highly stable, because now this is a tertiary carbocation. So you can see primary is converted into tertiary carbocation. And once this tertiary carbocation is formed, then the attack of nucleophile will take place from both sides, on the same side of. Now we don't have actually same side or opposite side, but yeah, two sides, and you'll get product. But this is unexpected product, right? It is a rearrangement product in this particular case. So if take this example, Br goes as a leaving group, you get a carbocation. This carbocation, this is the empty orbital. This empty orbital is used to take the pair of electron and shift this particular hydrogen from this carbon to this carbon. If it is shifted, you get a stable carbocation. A secondary carbocation is converted into tertiary carbocation, and then ethanol will react with this to give a rearrangement product. So such kind of reactions are where the reaction goes via SN1 mechanism, but you get an unexpected product because of the stability of carbocation. If by shifting a group from beta carbon to alpha carbon, if you are going to get a more stable carbocation, then generally a rearrangement product is observed in case of SN1 reaction. You will never find such kind of rearrangement in the product whenever SN2 reaction takes place. It is possible only because in the SN1 reaction you get an intermediate carbocation. So this is how we have now learnt about SN1. Then in module 2 we have spoken about SN2 reaction, and in this third module at the beginning we have spoken about Sni type of reaction, and then a special type of SN1 reaction where rearrangement product is obtained. Now let us again revise and understand how will I distinguish between SN1 and SN2 type of reaction. So the main factors, key factors to distinguish between SN1 and SN2 are nature of substrate, nature of nucleophile, and the type of solvent used. So if I take a substrate, I know that the substrate has two parts. One is alkyl part and another is a leaving group part. So the leaving group attached to which carbon, whether it is primary, secondary, tertiary, that will decide whether the reaction will go via SN1 or SN2. So we know that if it is a primary carbon, your leaving group is attached to primary carbon, then SN2 mechanism will take place. And if it is tertiary, then SN1 type of reaction will take place. If your leaving group is attached to allylic carbon, benzylic carbon, or if it is attached to tertiary carbon, then reaction definitely will go via SN1 mechanism because carbocation intermediate will be highly stable at that time. Similarly, if you are talking about nucleophile, we know the rate equation, and the concentration of nucleophile affects the SN2 type of reaction, but it is least affected. SN1 reaction is least affected because of the concentration of nucleophile. So generally it is observed that weaker nucleophile will favor SN1 reaction and powerful nucleophile will favor the SN2 type of reaction. Solvent, we are classified into two. You have a polar protic solvents and polar aprotic solvent. Polar aprotic solvents like acetone, DMSO will favor SN2 type of reaction, whereas polar protic solvents like water, ethanol will favor SN1 type of reaction. Solvent plays a very important role in enhancing the rate of SN1 reaction. It is observed that polar solvent favor this reaction, and many times SN1 reaction is also called as solvolysis reaction. If I use water as a solvent, it is called hydrolysis. If I use methanol or ethanol as a solvent, it is called as a methanolysis or ethanolysis, and in general we call them as a solvolysis reactions. So if I want to revise, yes, what kind of reaction? SN2 and SN1. So this is how we represent a substitution reaction. We know SN2 is a one-step concerted, SN1 is a two-step. Intermediate is not formed in SN2, but carbocation is obtained in SN1. Kinetic equation here, since it is a bimolecular, we will say rate is directly proportional to concentration of substrate and nucleophile. Whereas unimolecular, means rate depends only on the concentration of substrate. If we talk about stereochemistry, SN2 will always be with 100% inversion of configuration, and therefore such kind of reaction is called as stereospecific reaction, whereas SN1 will always end up with racemization. It is a non-stereospecific reaction. Now, the percentage of 2, that is with retention and with inversion, depends upon various factors. So product may or may not be optically active in case of SN1, but in SN2, product will be always optically active. Then we have seen nature of substrate, less hindered substrates, generally primary substrates, they undergo SN2 type of reaction, whereas those substrates which can produce a stable carbocation like tertiary, allylic or benzylic, they will undergo SN1 type of reaction. Living group depends upon both reactions, since their rate depends upon structure of substrate. Both get affected. What kind of living group is there will be affecting both SN1 as well as SN2 reaction. Nucleophile, we know that SN2 reaction depends upon its concentration of nucleophile, as well as strong nucleophiles will favor SN2, whereas weak nucleophile will favor SN1 type of reaction. If you're talking about solvent, we know polar aprotic solvents like DMSO, like acetone will favor SN2 type of reaction, whereas polar protic solvents will always favor SN1 type of reaction. It is also known as solvolysis reaction. So this is how we distinguish SN1 and SN2. We have just seen that in SN1 rearrangements are possible, in SN2 no rearrangement is possible. So with this we finish with our distinguishing between SN1 and SN2. This is how one can predict whether reaction will go via SN1 or SN2. Now there is a question where you are supposed to answer, understand all the details given. There is a hint also given, and if you click, you'll get the structure of product, and by looking at the structure of product, you can always try to write a mechanism for this particular reaction. So this is your assignment. Try to write a mechanism for this particular conversion, as well as answer these questions and try to revise